Hi Year 12s and welcome to the first video in a new series on circular functions. The idea is that this series is self-contained and covers the majority of content from the Year 11 course as well as the Year 12 course. In my experience, most students find circular functions to be a challenging topic, and so normally in class I do a lot of things on the board and give a lot of verbal explanations, and it's hard to take that all in at once. So I'm hoping that by providing these videos, if you need to go back and watch them again, they're there for you as a resource. So in this first video, we're going to review the radian unit for measuring angles, and in the next few videos we will look at symmetry properties of the unit circle and deriving exact values from first principles. So let's get underway. You don't need to know the definition of the radian as precisely as this, but it's worth stating. So if I draw a circle and I consider the arc length, which is subtended from the center, we're going to define 1 radian to be the angle such that the arc length, which is on the outside of the perimeter of the circle, is equal to the radius. So here I've got an example for a circle with radius 1. So here's the radius, and here is the arc length. If I set up the angle at the center so that these two lengths are exactly the same, then we're going to call that 1 radian. So in this first diagram here, theta is 1 radian. Now this might seem strange. Normally we measure angles with degrees, and we're used to 360 degrees being a full revolution. Calling this 1 radian, it'll seem strange if you're seeing this for the first time, but I claim that if we make this choice, it's actually going to make our calculations easier. So in fact, most of the work that will be done with circular functions from this point onwards will be exclusively with radians. Occasionally I will make reference to degrees just to strengthen a particular concept. Now, if we look at this second diagram here, you'll see that the radius is still 1, but I have now called the arc length L, and obviously theta is no longer 1. In fact, if I multiply the arc length by L to get from 1 to L, then I have also multiplied the angle theta by L, because there's a direct proportionality between the angle and the arc length. So in this second diagram, we're just going to say theta equals L radians. Now, if we choose to make this definition, we get a very nice formula for the arc length. And that formula is as follows. So now I want you to note that the circle no longer has radius 1. I have allowed the radius to be completely general, and I have called it r. So if I have a circle with radius r, an angle theta measured in radians at the center, which subtends an arc length, lowercase l, then I get the following formula. The formula is L equals r theta. So the claim is if I double the radius, I double the arc length while keeping the angle the same. Now let's see if this makes sense. If we were working in degrees, our formula would look like this. We would have L equals 2 pi r, which is the perimeter or the circumference of the circle, multiplied by the fraction of the full revolution, which is 360 degrees. And this, of course, assumes that the angle is in degrees. And now, if I just adjust this formula very slightly and simplify it, I get the following. I get pi over 180 times r times theta. And I'm going to suggestively write it like this. I'm going to write r first, times pi over 180 theta. And this suggests a conversion between the angle in radians and the angle in degrees. Of course, you've got to remember that theta in this first equation and theta in this second equation are different quantities. One of them is in radians and one of them is in degrees. Now, I claimed when I wrote down this first formula that arc length is directly proportional to the radius. And we see that's true if we go back to our formula in degrees. If I double the radius, I double the arc length while keeping the angle the same. So we're almost ready to define different angles in radians that we will use as sort of standard exact values for the rest of this course. So now I want you to imagine that I have a circle with radius 1. Of course, if I ask you to find the circumference of this circle, the answer is 2 pi, because it's 2 pi r, but r equals 1, so we just have 2 pi. Which means that if I define r equals 1 and L equals 2 pi, and use the fact that L equals r theta, I get theta equals 2 pi for a full revolution. Which means we will define 360 degrees as equal to 2 pi radians. Okay? Once we know this fact, we're ready to write down some familiar angles that you'll have seen in the year 11 course. So one full revolution is 2 pi. That's the circumference of a circle with radius 1. So if I want a half rotation, which is 180 degrees, I just need to take a full revolution and divide it by 2, which is pi. If I want a quarter revolution, divide by 2 again, and that gives me pi on 2. And to get from 90 to 30, I divide by 3. So that's pi on 6. If I want to get from 180 to 60, I divide by 3. So that gives me pi on 3. And to go from 90 to 45, I divide by 2. So that gives me pi on 4. These are your common angles. And it's very easy to mix up 60 and 30, pi on 3 and pi on 6, because they all have 3's and 6's in them. The way I remember it is to say 30 is smaller than 60. So between pi on 6 and pi on 3, I need to choose the smaller angle. And if I divide by a larger number, the result is smaller. So pi on 6 is less than pi on 3. And 30 is less than 60. Okay, so that's how I remember it. Okay, let's conclude with some formulas for converting between these units. For this video only, I will use the symbol lowercase c for radians. If you don't see that symbol, it's implied that the angle is measured in radians. We always write the degree symbol if we intend an angle to be represented with degrees. So we know this as a fact. So if I want to go from degrees to radians, what I need to do is divide both sides by 360. So that gives me that same factor, pi on 180, which we saw when I argued that this angle and this angle is the same. Okay, so that hasn't come from nowhere. Now, if I know the angle is, say, some angle theta in degrees, then what I need to do is take that number theta and multiply it by pi on 180. And now it's in radians. Okay, now if we choose to go the other way, I can say that 2 pi radians is 360 degrees. And now what I'll do is divide both sides by 2 pi, sorry, I should say. So if I do that, I'll get 1 radian is 180 over pi degrees. Which means if I have theta radians, that's going to be the same as 180 over pi times theta degrees. And I know that's a bit complicated, so I think I'll simplify it by writing it like this. So if I have the angle in degrees or radians, here's what we want to do. To go from degrees to radians, we are going to multiply by pi on 180. And to go back, we multiply by 180 on pi. Since we know this definition, 2 pi radians is 180 degrees, 360, I should say, or pi radians is 180 degrees. So if you have this fact memorized, you can always rederive this relationship in the future. Alright, I'll see you in the next video. Thanks.